Section 11.1.17-T. In randomized, double-blind clinical trials of a new vaccine, toddlers were randomly divided into two groups. Subjects in Group 1 received the new vaccine, while subjects in Group 2 received a control vaccine. After the second dose, 121 of 379 subjects in the experimental group, Group 1, experienced nausea as a side effect. After the second dose, 150 of 595 of the subjects in the control group, Group 2, experienced nausea as a side effect. Does the evidence suggest that a higher proportion of subjects in Group 1 experienced nausea as a side effect than subjects in Group 2 at the alpha equals 0.10 level of significance? Okay, now to determine if a higher proportion of subjects in Group 1 experience nausea as a side effect in subjects in Group 2, perform a hypothesis test regarding the difference between two population proportions. Now, if you notice, I color-coded Group 1 and Group 2, just so that we can see the difference between that when we look at our information from the problem. So, we have subjects that are in Group 1, okay, that received the new vaccine, okay, and then also we can see that after the second dose, okay, 121 of the subjects in the experimental group of Group 1 experienced nausea as a side effect, okay, and then we know that the subjects in Group 2 received the control vaccine, okay, and then after the second dose, 150 of 595 subjects in the control group experienced nausea as a side effect. So we're going to let P subscript 1 represent the population proportion of toddlers in Group 1 who experience nausea. We're going to let P2 represent the population proportion of toddlers in Group 2 who experience nausea. To test hypothesis regarding two population proportions P1 and P2, the requirements below must be satisfied. Where N1 is equal to the sample size for sample 1, P hat subscript 1 is equal to X1 divided by N1, where X subscript 1 is the number of individuals in sample 1 who have the specified characteristic, capital N subscript 1 is the population size corresponding to sample 1, and N subscript 2, P hat subscript 2, which is equal to X subscript 2 divided by N subscript 2, X subscript 2 and capital N subscript 2 are the corresponding values for sample 2. Okay, the following requirements must be met. The samples are independently obtained using simple random sampling or through a randomized experiment. We have the following. Population for 1, population 2. We take N times P hat times 1 minus P hat is greater than or equal to 10. Same thing for population 2. And then N subscript 1 must be less than or equal to 5%, meaning the sample size is no more than 5% of the population size. This requirement ensures the independence necessary for a binomial experiment. And the samples are independent since the toddlers were randomly assigned to the treatment and control groups. Okay, so the first thing is that the samples are independent since the toddlers were randomly assigned to the treatment and control groups. Okay, so now what we're going to do is we're going to identify the information needed for Group 1 and then the information needed for Group 2. So we know that X subscript 1, which is from Group 1, is 121 from our here, so we know this is 121. And we also know that N1, which is the population size, is out of 379. And we got to figure out what is P1 hat. Okay, we know that X subscript 2 is equal to 150. We know that the sample size for group 2 is 595. And then P hat subscript 2 is what we're looking for. Okay, so to find X subscript 1, to find P subscript 1, P hat, we know the formula is X subscript 1 divided by N subscript 1, which is equal to 379. Correct that? It's equal to 121 divided by 379. And then P hat subscript 2 is equal to X subscript 2 divided by N subscript 2, which is equal to 150 divided by 595. Okay, now that we have this information, now we want to check and see if N subscript 1 times P hat subscript 1 times 1 minus P hat subscript 1 is greater than or equal to 10. So let's go ahead and do that. So we know that we have N subscript 1 times P hat subscript 1 times 1 minus P hat subscript 1 needs to be greater than or equal to 10. Okay, so we know this is going to be 379 times, that's 121 over 379 times 1 minus 121 over 379. Okay, which needs to be greater than or equal to 10. And so we end up getting approximately 82.33. So we know this is satisfied. Okay, and then we're going to take N subscript 2, P hat subscript 2 times 1 minus P hat subscript 2 to make sure that's greater than or equal to 10. So what we have next is the following. We have 595 times 150 over 595 times 1 minus 150 over 595. I'm going to make sure that's greater than or equal to 10. So we get approximately 112.16, and therefore that is greater than or equal to 10. Okay. Now, if we also take a look at the sample sizes, okay, because we want to make sure the sample sizes is no more than 5% of the population. Well, the sample sizes are less than 5% of the population size because the sample sizes of 379 and 595 are less than 5% of the population of toddlers. So what we can say now is that all three requirements are satisfied, so we're going to proceed to conduct the hypothesis test. So in this case here, we want to then be able to determine, okay, what is our null and our alternative hypothesis. Okay, so again, the null hypothesis is a statement to be tested, and a null hypothesis is a statement of no change, no effect, or no difference, and is assumed true until evidence indicates otherwise. The alternative hypothesis is a statement that the test is trying to find evidence to support. Now, in this case, the test is being performed in order to determine if a higher proportion of subjects in group 1 experience nausea as a side effect than subjects in group 2. So remember that P1 represents the population proportion of toddlers in group 1 who experience nausea, and P2 represents the population proportion of toddlers in group 2. So if we're saying that P1, okay, is going to be higher, meaning greater than, so does evidence suggest that the higher proportion of subjects in group 1 experience nausea as a side effect than in groups 2? So we know that the null is going to have the equality, so it's always having the equality, so P1 is going to equal P2. And according to that last sentence in the question, the claim is that P1 is going to be greater than P2. Okay, so what does that tell us? Well, that tells us that because it's greater than, we know it's going to be a right tail. Okay, and in part 4, we want to be able to find out what is the significance level. Well, the problem wants us to find that level of significance to be 0.10, so we know it's going to be 0.10. Okay, so for number 5, what we want to be able to do is we want to be able to find the test statistic. Okay, so in order to do that, we want to be able to use the following formulas. We want to be able to find p hat, and we also want to find our test statistic. So let's go ahead and just make sure that we know what our information is. Okay, we know that P1, okay, is our value here, right? And we also know that this is x1 and this is n1. Okay, and then we also know that we have p hat 2. So there is that one and that one. We know that's n2 here. And we know that this is n1. Okay, so let's go ahead and find our answers here. So here, what we're going to do is we're going to take x1, which is 121, plus x2, which is 150, and then we're going to divide that by 379 plus 595. Okay, so if we add that together, then we're going to get 271 divided by 974. Okay, now if you notice, I kept these in fractions. Now we can simplify this and round it to 3 decimal places. But when we plug it in to find our test statistic, we want to make sure that we have the exact number so that we're able to round it. So we don't want to create any kind of errors by rounding first. You can, but when you're doing this by hand, it's a better way to be able to do that by just leaving it as in fraction form. So in this case here, we want to find the test statistic. So the test statistic is going to be, we have 121 over 379 minus 150 over 595. And then we're going to divide it by the following. We're going to divide it by the square root of 271 over 974 times 1 minus 271 over 974. And then we're going to multiply that by the square root of 1 over sample size 1, which is 379, plus 1 over the sample size of 2, which is 595. Okay, now let's plug this into our calculator. So when you plug it in your calculator, you want to make sure that you're including parentheses. So what I mean by that is, okay, so we're going to use parentheses here, and then we're going to put parentheses around here inside the parentheses, and then parentheses here under the radical. Okay, it just doesn't create any kind of mistakes with order of operations. So let's go ahead and do this. So we got the numerator. The numerator is parentheses 121 divided by 379. parentheses, and then minus, we have 150 divided by 595, parentheses, press enter. Now this is in the numerator, and we're going to divide that by what's in the denominator. So we're going to divide it. We got a parenthesis, and then we're going to put in the second square root of 271 divided by 974. Okay, and then we're going to put that in parentheses. Times 1 minus parenthesis 271 divided by 974. And then we're going to move to the right to create a new square root symbol. So second square root, we got parenthesis 1 divided by 379, parenthesis, and then plus, we have 1 divided by 595 with parenthesis. Here, go to the right and then close the parentheses for the denominator, and then we're going to hit enter. And now that we hit enter, we're going to be able to get our test statistic. So here is our test statistic, and we can see that we get the following. We get 2.28. So rounding that to 2 decimal places, we get 2.28. Okay, now the next thing we want to do is we want to be able to draw our diagram. Okay, so what does our picture look like? So in step number 6, we want to be able to draw our bell curve. Okay, so here is our bell curve. Okay, we found our z-score, so we know that the mean is going to be 0 here. Okay, and then we found our test statistic to be 2.28. So recall that this is greater than. So if we have here 2.28, we want to be able to find the area to the right of that, which means that we're looking for the p-value here. Okay, so we can either use the function on our calculator, or we can use the table. Okay, so if we want to find a p-value, we can first determine, okay, how do we find the p-value using the table? Well, remember that the table for z-scores gives you the area to the left. So that means here, we're going to have to subtract, we're going to take 1, right? So if we're using the table, it's going to be 1 minus the p-value to the right. So it'll be 1 minus the p-value of 2.28. So what is the p-value of 2.28? So we're going to go down here. Okay, so here is 2.2. So let's go ahead and highlight that. So there is 2.2. And there is 8. So 2.28 gets a p-value of 0.9887. So 1 minus 0.9887. So let's go ahead and put that in our calculator. 1 minus 0.9887 is equal to 0.0113. So that's equal to 0.0113. Now, if we wanted to use the calculator function, we would use normal CDF. So in order to do that, we're going to go second distribution, go to normal CDF. We know that our lower value here is 2.28. We know that our upper bound is 9999. We know that our mean is 0. We know that our standard deviation is 1. So let's go ahead and do that. So we have 2.28 0.9999 with a mean of 0 and then 1. And so what do we get for our p-value? Go ahead and paste, press enter, and you're going to see that we get the same value there. So whether using the table or using the calculator function, we end up getting the same p-value, which is 0.0113. Okay, and then make sure I wrote here is just 2.28, not 2.21. Now we want to be able to interpret the p-value. Okay, so if we round this to 0.011, okay, so let's say that we round this to 3 decimal places, which is 0.011. Now, if we notice that the last one is going to be in the thousands place. So that means if we wanted to write this as a fraction, this is going to be 11 out of 1,000. Okay? Just so that we can interpret this. So if we want to interpret the p-value, again, the p-value is the probability of observing a sample statistic as an extreme or more extreme than the one observed under the assumption that the statement in the null hypothesis is true. If the population proportions are equal, one would expect a sample difference proportion, the one observed in about 11 out of 1,000 repetitions of this experiment. Okay, now we're going to go to step number 7 because we want to be able to compare the p-value to the significance level. Okay, so in order for us to figure out what the conclusion is, okay, so for step 7, if the p-value is less than alpha, then we're going to reject the null hypothesis. Otherwise, do not reject the null hypothesis. Well, if we round our p-value to 3 decimal places, we have 0.011, okay? And going back to step number 4, our significant level is 0.10. So, what do we see here? Well, we can see here that this value is less than the significance level. So, therefore, we're going to reject the null hypothesis. So now we can go ahead and then write down what our conclusion is. So from here we can say that there is sufficient evidence to conclude that a higher proportion of subjects in group 1 experienced nausea as a side effect than subjects in group 2 at the alpha equals 0.10 level of significance.